Massachusetts. In the early days when Henderson opened the one man, one phone consulting unit long time ago, more than half a century ago. So today, we will have Matt talking about the research not done at the consulting company, but the work done before he joined the consulting company. And it will be also interesting that Matt is the very first speaker and probably the last speaker in our lecture series that's going to wear a suit to give a talk.
Wow, I didn't realize that was such a novelty.
Yes. Yeah, so it's great. So with that, I'll give the rest of time to Matt.
All right, well, thank you very much. First, I should say that yes, this has absolutely nothing to do with my company. This is only with my academic research. It's a very important disclaimer. Otherwise, my company will be unhappy if I don't make this very clear as well, possibly. Right, so that's really, we've already outlined the end result of this talk. So if all you care about is the end result, you can just like look at this slide and go to sleep. There is the issue with we can start, we know fluid dynamics, we can model that in a computer, we can model the heat equation in a computer, but then we have to try lots of different starting parameters for all the constants in the equations of heat propagation and fluid dynamics, which is very difficult, right? So it's very difficult to just run a computer simulation and say when it predicts tectonics. So really, that's why we arrive at this geochemical observation approach, which is what I've been doing. So that's how basically my real target of study is plate tectonics, but I'm actually going through this geochemical observation technique. So instead of having a big supercomputer and doing lots of fluid dynamics and seeing when we start getting tectonics in the computer, all we basically did, we look at old rocks and see when the rocks get very different, right? Because you can imagine if you had one type of rocks when the Earth is very old, and then suddenly transforms, then that's probably the start of plate tectonics happens, right? Because plate tectonics will have changed the surface rocks very rapidly. Of course, if you're looking at very old rocks, you have to make sure to ignore like all the alteration and all this extra noise that's introduced. So the really sort of fundamental work was done by Taylor and McLennan back in the 80s on this. And basically what they did a survey of a lot of shale in just all sorts of rocks they could find on the continents, right? And they plotted all these elements, and they basically said, like, look, very old rocks, there's this one composition, then you have 2.5 billion years ago, and then it changes into something that resembles the modern. So probably plate tectonics started about 2.5 billion years ago, right? I mean, you can buy this. It doesn't really, it makes sense, right? And since then, there have been a lot of very respectable studies that also they use different elements. So as you can see here, this is using, for example, thorium scandium and, light rare earths or heavier rare earths. But then these other, there have been many studies in the literature, and they all sort of agree that you did not have plate tectonics at first, right, in the very old time, before 2.5 billion years ago. So you probably had a mafic Archean Earth. But then you had 2.5 billion years ago, and then plate tectonics started, and then you had a very new setup, right, with something resembling plate tectonics of the modern Earth. So that's a general thesis here, and that's kind of what we're looking here. So it's interesting, all these studies, point towards a mafic Archean. But then when we look at titanium isotope study, which is actually the first study I did in my PhD, it was kind of a lucky start. I started my PhD and immediately started work on something very interesting. Then what you see here is we have a very different result. We actually look, if you're looking at 3.5, we actually see there is a lot of felsic in the very old Earth. So as you can see, it's actually very similar to the modern proportions. And the actual concentration of silicon dioxide in the Earth has probably not changed much either, according to these titanium isotopes, which is interesting because it suggests that, okay, maybe plate tectonics has actually been operating on the Earth since 3.5 billion years ago, right? That would be completely different to what all these other studies do, right? So it's interesting because if you look at ratios of elements, they tell you mafic Archean. You look at titanium isotopes, they tell you felsic Archean. So, okay, what is going on here? And simple answer could be that maybe there's something not quite right that we're doing with the ratios, right? Maybe we're misinterpreting something, or maybe just something slightly off. Because titanium isotopes, titanium is really hard to mobilize, it's really hard to alter. you would expect follow along and not fall asleep as you go through our general approach. So we're going to cover the sort of the n-member mixing model, which is what we use. We're going to then also look at some of our filtering methods, which we use to filter bad data from a data set. And also at our Markov chain Monte Carlo method, which is what we've done to basically propagate errors in our analysis. So, the question is, how do you reconstruct the continental crust? Because it's difficult, right? I mean, a bad idea is to just measure every rock on the continents and just average the composition of every rock, right? But the problem there, of course, is there's not enough graduate students to be able to do this whole thing. So, maybe a better idea is you measure just the composition of some rocks on continents, right? And then you just take the average of that, right? You don't do the whole thing, basic sample statistics. Because the issue there is, you have this thing called sedimentology, right, which exists on the Earth. So, like, just when you measure the composition of a sediment, the elements in the sediment are different from the elements in the, that originally were in the continents before they got broken down by wind and water and so forth, and later became that sediment, right? So, otherwise, sedimentology would not exist, and every rock on the Earth would be igneous, right? So, really, we want to be able to just measure, some rocks. We don't want to be measuring all the rocks on the continents, but we also want to make sure that we're actually measuring the correct things which don't change, and then somehow manage to figure out what was the original composition of just those igneous rocks that made up the continental crust. And that's where this member-based reconstruction comes in. So this is the basic idea here. It's basically a mixing model. And the basic assumption is we assume that there are some very important extreme compositions on the Earth. We call these are end members, right? Because they're the end of this mixing spectrum. And then we also assume that some ratios, for example, in this case, thorium, scandium, nickel, cobalt, actually stays the same, even if you have sedimentary processes and rain and erosion and all that, right? So obviously something like calcium, it will become very different if you have a lot of erosion and rain and so forth. But the key here is to pick the correct elements which stay the same. So in this case, the thorium, scandium, nickel, cobalt, right? And then what you can do, you can just measure like a shale, like a sedimentary rock. We use shales because they will have covered a large area. A lot of different rocks will have come from there. Like basically, a lot of different source igneous rocks will have gone into that one shale. So when you measure the one shale, you're actually also looking at a very big average. And then if you were to measure this shale and you see that its nickel cobalt is at 7% here, right? And that its thorium scandium is about 1%, and you assume that these are the compositions of your end members, you can do this, it's a pretty simple mathematics to figure out what percent hematite, what percent mafic, what percent felsic you need to recreate this shale, right? So in this case, we would have about, if the shale was measured here, we would have like 10% hematite, right? And then we would have, let me get this right way around, 70% felsic and 20% mafic. And so then we would say, if this shale was representative of everything, then the continental crust was 10% hematite, 20% felsic, 70% mafic at that point. Right? There's a couple of, and these assumptions are important, are that we know the composition of these extreme end members, and that we also, that these ratios did not change very much between the igneous rocks and the sediments, right? Those are the key assumptions here. If you're good with that, then everything else will basically make sense, right? And then you can also actually reconstruct every other element from this, because once you know that you have 10% hematite, 20% felsic, 70% mafic, for example, then what you can do is say, I know that you're not going to use calcium, right, in the shale, because the calcium in the shale will have been changed. But if you know what the calcium is in hematite, mafic, and felsic, you can do that mixing calculation and actually compute the, for example, calcium, or even these, basically all the elements. You can get this giant Excel table where you have the compositions of everything. And that's basically what we did on paper, and we attached this table as well to the results, right? So how do we pick our members? Basically the logic here is just, you need something very varied igneous rocks, right? So you can have mafic and plus felsic, but you probably want to add hematites as well, because those are very weird rocks. They're much more enriched in certain elements. So even a little bit of hematite changes your chemistry a lot. So you want to have mafic, felsic, and komatiite is what we went with. And just to make it more detailed, we know that the composition of igneous rocks evolved through deep time. So when we're doing this mixing calculation at 3.5 billion years, we make sure to use old member composition of like old mafic, old felsic, old komatiites, and there's no such thing as new komatiites. You get the idea. Whereas if we do this composition reconstruction, this mixing model in the modern, we use very modern mafic and felsic compositions. So, and this will actually be a very important point, right? So, I mean, this was our general thing that we did in our paper. And you can see we had to use multiple databases here because we need something for the shales, right? We need to measure the shales. We also need to measure, which was this ORTES database we constructed. We need to measure the igneous rocks, right? But then we need to do a little bit of things, like we need to do some filtering to make sure that the data we have on our database is not bad. Then we need to calculate the error bars. Then we need to pick the best ratios. And then we actually do our final error propagation, right? So this is where the data science part of everything comes in, and the sort of computational part. So some of these are pretty simple, like igneous, the databases of igneous rocks are pretty good. So we just do a very basic check of like, do the major elements sum up to near 100%. So that's pretty simple. But then shales are pretty complicated. So we actually use this thing called local outlier factor, which is an interesting algorithm. This is obviously not geological data. This is example data. But it basically, it's an algorithm for detecting samples that are very far away from their neighbors, right? So, and it will work no matter what your distribution is, right? So it does not make an assumption of like the data is normal or the data is a particular way. Basically, this will just detect if your data point, right? If your composition of your one rock, it then compares it to the like basically distance to other rocks. And if it's really far away, then we'll say, hey, this one rock is super different from the other rocks. It's probably an outlier, right? And that's basically how we kick out these shales in our database that we think are wrong. We use this local outlier factor filter, and it automatically detects, like we don't have to give it any preconditions really. It just automatically runs to detect which shales samples are just super different. And if they're super different from the other rocks, then we just kind of say, okay, it's probably bad data. We can kick it out, right? So this is not much used in academia, but it's very, very popular in sort of commercial data science. So I've definitely used it after leaving academia. And these are the basic equations. We don't have to go through the details of it. If someone has a question, we can look at these. But the point here is to, the main principle here is if a rock is far away from the other rocks, that's when it will get flagged as an outlier. Right, so that's kind of the filtering done, right? So we started with these databases, and we made sure to filter it. So now we only left with good data. So now we have to figure out how do we get uncertainty on this, right? Because obviously, answer in science is never 100% certain. And if we look at the data we have, even though this is just good data, right? All we have is a lot of noise, right? We don't have for one time. We don't have just one value, which is what we're going to need in our model. So, I mean, how are we going to use this, from this noisy lots of data points, how do we get a single value for each time? You can use a moving average, right? And then you get you do a moving average through time and you get a curve like this, right? Which is fantastic because now you have like a single value instead of having lots of these values, right? You have one value which can go into your model. But then, of course, the problem is, the very big problem, which is taking like the moving average, is like there's absolutely no way you can calculate error bars in here, right? It's just impossible. There's nothing defined here. So what we do is we use this algorithm called the Bootstrap algorithm, which is a very interesting algorithm because it will work with anything, right? Usually when you're computing like error bars, you need to assume, okay, data is like normally distributed, or you need to assume there is a known distribution, right? Or you have to make a very strong assumption. But with the Bootstrap, you can do this to estimate basically error in any model. It doesn't matter what it is. And because the distributions, in geology, it's a natural system, it's very complex. So we don't want to assume anything. So here instead, we can use basically this data-driven approach to calculate our errors. Okay, now Cortana popping up. Yes, nice Cortana. So we can use this algorithm to calculate our errors, and it will work very well. What we do is we take our data, we fit the moving average model to it, and then we resample with replacement, right? So we basically make a new data set from the original data set by picking randomly the same amount of points that we had in the original data set, but we pick them randomly, right? Therefore, some points will be more selected in the new data set than they were in the old data set, and some points will not be present in the new data set. So even though we pick randomly with no bias from the old data set, our new data set will be slightly different than the old data set. And then we fit our model again to the new data set, right? And we can do this like 10,000 times or 1,000,000 times if we want. And we get like, say, 10,000 models that are all slightly different because they were all fitted on slightly different data. And then once you have these 10,000 different models, you can just at each time, you can calculate how much variance is in the answers between these different models. And you get these beautiful error bars, right? And you can see these error bars, they do actually change with time. It's not like there's a single value for every time. We have less error when we have more data here, which is more close together, and we have more error when there is less data, which makes a lot of sense. That's exactly what you expect. So now we figured out how we get our data clean. We figured out how do we get error there. So now we need to figure out how do we actually use the error with our clean data, and how do we actually get our final result, right? How do we go? We have these shells, we have the we have the members, and now we actually have to mix it. And to do that, we do this Markov chain Monte Carlo. So obviously we'll go to Monte Carlo, which is a fabulous place. Absolutely recommend it if you've never been there. And just to this is just a slide to show the power of these random methods, right? Because Monte Carlo is all about gambling, right, in the city. And Monte Carlo, the mathematical approach, is also all about gambling, i.e. randomness, right? So here, this is a very interesting experiment from the 18th century to calculate the value of pi, right? You draw some lines on the paper, then you throw matchsticks on it, just randomly. And you count in how many times you've thrown the matchsticks, and how many times it hit a line, right? And then you do 2 times the number of throws divided by the number of hits, and you approximate pi. So here we have 17 throws, 11 hits, and it just goes up to 3.1, which is about pi. And if you do this like millions and thousands, thousands of millions of times, you will converge on the correct answer to pi, which is fantastic, right? So this is just like a slide to show the, power of these sort of methods involving randomness, basically. So Markov chain Monte Carlo is this algorithm that uses Markov chains which are basically, random mathematical objects, but they are semi-random. So they're kind of going to follow a certain distribution. And if you just you construct this Markov chain and you let it run for a long time, you can actually sample that distribution of the states that this Markov chain has visited, and then you see what the resulting distribution is. And that will actually resemble, if you've set things up correctly, and if you're using the correct error function and so forth, you will actually figure out the distribution of your error, given if you have the input errors, right, of the uncertainty in your data, and you have a mathematical model, and you run the mathematical model through this Markov chain, you'll actually get the result of the model along with how much uncertainty there is, which is, again, a fabulous method and works even for nonlinear systems. So this is kind of the model what we're using, right? This is our error function. It's a chi-squared distribution, which is basically, this is the output from our model. This is the data. This is what the ratio we observe in the shells, something like thorium-scandium or nickel-cobalt. And it's just normalized by the variation in that ratio, right? So if a ratio, for example, if nickel-cobalt typically has more variation than thorium-scandium, so, right, it's more noisy. So we want to give less attention to the more noisy ratio, and we go on to give more attention to the less noisy ratio. So that's why we're dividing by this variance here. And this is basically our mixing model. This is like proportion of Komatia, proportion of mafic, proportion of felsic. This is the value of the ratio in a komatitic rock, felsic, mafic rock, felsic rock, and the value of the denominator as well. So you can imagine this is nickel, nickel, nickel. This is cobalt, cobalt, cobalt. right? And then you do this equation. It's just a straightforward mixing model, and you get your calculated ratio, which you can then compare against the observed rate ratio. And if you rewrite this equation, if you can rewrite it in this way, you'll see there is actually a very good analytical form for this variance factor here. Because the variance factor is a bit difficult to compute because you have error in your sort of x coordinate. You have error in the you have error in your y coordinate, which is your shell, right? Obviously, you have error in there. But you also have some errors in your model. You also have, you're not certain about the composition of the mafic and the felsic and the chromatid. So you have to consider the errors of all these. And basically, that's what we've done here, is effective variance method. You see we have the error in the felsic, the error in the mafic, error in the chromatid, and error in the shell all put together. And this is the correct way to weigh these errors if you're actually using this. So you have to apply this effective variance method, right? So you see we have these weighing factors here. So that's basically, if you go through the fundamental, it's all math, that's what you end up with. And it's actually very quick to put this in. We use C++ for this, right? Because we're doing millions of iterations. So you don't want Python, you want something that's pretty fast. So we use C++ because that's fast. And you can see it's very short, right? So there's maybe some scary equations, but then actually it's very, very quick to write. So it's very convenient. And now to actually move the Markov chain around, we use what's called this Metropolis Hastings algorithm, which basically each time we start at a certain value. At first, we should start with a guess of what we want the reconstructed value to be, something like 33% chromatite, 33% mafic, 33% felsic. And then we make a slight difference, right? We move that guess slightly. So we say something like now it's 34% chromatite, 32% felsic, 33% mafic, right? And then we calculate the likelihood of the new state using this equation that we just used here, right? And then you can compute the ratio between the new state and the old state likelihoods. And if the new state is more likely, the Markov chain will always go there. But if the new state is less likely, i.e. the value of this error here is bigger, then we're going to have a certain probability to transition, right? And then basically, like, we don't record the first few iterations to let the system settle in. And then we compute the statistics on the system. And again, you can see this is very, very quick to put in computer code. But if we do things this way, what we're actually going to end up with is our final result, right? So this takes a lot of, like, you know, this is something that's quite an advanced result that, like, you have to spend a lot of time. And if people want me, I can go through this, but it's kind of a very complicated statistics. But even though the theory is complicated, the practice is actually extremely simple. As you can see, like, this entire complicated statistical thing is just on one screen here, basically, right? Along with chi-squared, which you had on that previous screen of code. And this actually allows you to get your final result from the mixing model with errors, right? Assuming that you have the errors in your end members and the errors in your shell data. And, you know, you manage to reconstruct, you basically find what the proportion of these end members, you know, what percent felsic, what percent chromatite, what percent mafic, to best explain the observed sedimentary composition in the rocks, right? But there's still an issue here, and that's like what proxy ratios are the best, right? Because as I mentioned earlier, you want to use proxy ratios which do not change between the original rock, the igneous rock, and the sedimentary rock that you actually measure in your shells, right? So you need something that is insoluble and something that is also very incompatible. Therefore, it won't get changed by, you know, sort of aqueous processes. And also won't just have gone through like a lot of like other chemistry as well. So if you look at these incompatible and very insoluble rocks, you're gonna see you have a bunch of stuff like these elements. So we basically pick these. We don't want to pick all the rare earths, right? Because they're just so close together, it doesn't make sense. So we basically pick these as saying, okay, these are going to be good elements. We still don't know what the perfect combination of them is, like how to arrange them into the best ratios, but we know these are good elements, right? Just from common sense. So don't use algorithms here, just use common geological sense, right? Now the problem is, there's a lot of ways to arrange these ratios, right? Actually millions and millions, right? So you might think, okay, are we going to use some clever algorithm here to figure out what are these best combinations of, like, if we have two ratios, what are the best combinations of ratios to use here to, produce the lowest error basically in our system. Or if we have 5 ratios, what is we have to go through 8 million of these combinations. So what we can do, we could be very clever, right? But that's not what I did. Instead, University of Chicago has a big computer, right? Big supercomputer. Any good university has those. So you just tell the supercomputer, hey, I have all these ratios, right? I have all these millions of combinations. Try out every single possible combination and just tell me which one is best, right? It'll take a couple of days, but I don't care. I can go on the weekend. I can just go, have fun, and then come back on Monday, and the supercomputer will have gone through all these millions of combinations, and then at the end it gives me the answer. I know, oh, okay. So if I'm using 8 ratios, this is how to arrange them to get the lowest error, right? And to figure out the lowest error, just like I cited here, this is how we told the computer to decide, right? So again, we have our mixing spaces for different sets of ratios. Here we have thorium, scandium, this is nickel, cobalt, which is a very nice mixing space. And here we have nickel, cobalt versus chromium, vanadium, which, as you can see, is kind of a messy mixing space, right? And these error bars here, that's not the error of the shell. So you can see if we have like 1 standard deviation in the shell here, it changes the proportion of the Kamatia mafic Ptacek a little bit, but not a large amount. Whereas if you're in this mixing space and you have 1 standard deviation, it can like be a very significant impact, especially somewhere like here. It can very much change the answer, right? So that's basically how we quantify it. What is a good mixing space versus a bad mixing space? How much, if you change your shell by 1 standard deviation, how much will the observed calculation of mafic Ptacek Kamatia change, right? And that's how we did that algorithmically. So that's basically our entire method. That's all we've done here, right? And that was quite quick, obviously. I can go back if people have questions and go through things in more detail. But then, about like one only thing to call out here again is that rocks weren't always the same through time. Rocks were different in, old days versus like new days. Like, for example, you had more TPGs for the felsic rocks in Archean, but now it's just a modern granites. So actually, this makes this is a very important consideration, because if you think that like, hey, rocks are always like felsic rock is always the same, you're actually going to have a result that there's a lot of mafic rock in the Archean, right, in the system. Whereas if you assume that, okay, rocks change through time, you're actually going to figure out there's a lot of felsic in the Archean. So this was a very important assumption and like a very crucial element of the model. That's why we're calling it out here. And yeah, ultimately, that's how we get to our result. That's how, I told you where the data comes from for this, what we've done with the data, right, to make it clean. Then how we calculated the error bars, as well as the best fit, and also how we decided which combinations of ratios are the best. And, obviously our results are quite different to what we had before in terms of, because our conclusion is plate tectonics are operating for a long time. Conclusions of a lot of prior literature are, plate tectonics are only operating since like 2.5 rather than 3.5. So that's an entire billion-year difference. But really, if you look at the details of these other studies, and here, just for example, I've got a Tangadal paper, this is our paper. See, and you look at the magnesium. So even though they claimed that, plate tectonics were operating for, a billion years difference there, basically, you can see that if you look at our magnesium composition at around 3.5, we predict that it's 2.5 times the modern composition, right? If you look at them, they're predicting, 3% now, and kind of, so if you do like 3%, 2.5 times that, that's obviously, it doesn't quite match up, but it's not super far away, especially if you consider these error bars are very large, right? So what we're proposing is slightly different than Tangadal. We're not saying the same thing, obviously, because you can see the error bars don't match up. But we are not completely different either. And the difference, because we are a little bit different, that difference comes from having the, basically better filtering of data, we would say. I think we probably had the most advanced filtering algorithms of the other studies we reviewed in literature. And also having basically trying out lots of different ratios, so proxy ratios, to find the best ones. which I think we've also done the most extensive study of these mixing ratios, like to pick which mixing ratios are the best. And I mean, really, you see the difference here. So they were predicting, they said between 40 and 80%, basalt in the RPN, right? Which is a very big error bar here, and about 10 to 40% granite. Whereas R, you can see again, I mean, we don't quite fit in the error bars, but if you look at sort of 40% granite versus 50%, it's not a massive difference. And they have very big error bars, which is fair, because the system that we're using is fundamentally, it's very tricky to use. So they did a very good work in doing it that way. But because we are more selective with our ratios, we selected ratios which lead to smaller error bars. So that's why the error bars here are smaller. And that's effectively why our results are different from their results. It's the combination of all this particularly advanced filtering and being very careful with your error bars and making sure you don't make assumptions to use these non-parametric methods. Also making sure you do the selection to find the best parameters for your system. And you put all that together and that's what you get. So further work, I mean, I'm out of academia now, so I'm not working on this anymore, but I'll be very interested to see what academia comes up with this, after me. So I'm not going to work on this anymore, but I'll be very interested if there's someone who does. Yeah, that's about it. If people are interested in data science, this is my LinkedIn. You can feel free to reach out. But otherwise, I can just take any questions.
Great. Thank you very much, Matt. Now it's time for questions. Actually, I have questions to start with. That after you selected about 16 elements and then you try to combine with a 2-to-2 ratios. So have you been thinking of other combination of elements? I mean, this is 16 elements. Basically, this is P16. Yeah. There are so many possibilities. Although you I understand why geochemists like ratios, because we like ratios, because that's the way that several elements that behave together, or they don't, or they behave in different directions. So what is the point on that? Since you have also, although you have listed many possibilities, but also the total number of possibilities out of a combination of 16 elements is much bigger than the ones that you have listed, about 2 to 3 million possibilities.
Oh, you mean the total amount of combinations here would be bigger than what I say here? So you had multiple questions here, but I can take those in order, right? I think first,
Yes. Yes. The total number of combinations is much bigger than 2 million.
Yeah. Especially if we considered many more elements from here or something like that, right? If we didn't include ratios, if we just considered elements on their own as well, right? That's kind of, am I understanding your question right?
Yes.
Yeah, I mean, I agree with you. The total space of possibilities is much bigger, right? And we're actually looking at a pretty small number of possibilities. But I mean, the reason we get this here is already, even with a small limited set, it's already a lot of combinations, right? And it takes quite a bit of computational time to go through everything, right? So we wanted to narrow it down for that reason, just practical reason, that there is a computing time, and just time, research time is limited. So we have to focus our research a little bit. We can't just look at everything. Other reason is there's a lot more elements, but some of these are pretty bad. It's pretty hard, in terms of not just they're soluble or something, but also iridium is not very soluble, obviously, right? But iridium is very difficult to measure. So not many people bother measuring it. Therefore, in the database, we have very few entries for iridium, right? And also, iridium is very small concentrations. So it's just gonna have a lot of error in it in terms of it's just very difficult to measure, right? So there's just elements you want to exclude for that. And obviously you could push this box out here, you could include more elements slowly. But we decided this was the best trade-off between, having the elements that we know that are best, but still considering enough elements that we can try out enough combinations to find something that's actually good, right? So obviously, if we put the box all the way here, we only included thorium and niobium, then we have no choice, right? Because there's only one combination, thorium over niobium. So we have to make the box a bit bigger, but then we just have to stop it somewhere, So that could be further work, is you can push this box, make it bigger, and try to do more calculations. But you're going to run into these issues that like geochemical databases are incomplete, right? And that a lot of these elements are actually quite difficult to measure in the databases.
Okay, then I have a following question that even for the limited 16 elements you list, I believe that in the data sets that you organize, there must be missing values. So how do you treat those missing values? How do you assign new value for them? Or you just give it a value like 0? Or how do you deal with that when you calculate?
Yeah, so that's actually one of the beauties of this method. So if you look at this, this is our error function effectively that we're minimizing, right? To find the best fit between our reconstruction, the reconstructed and observed ratio, we basically minimize that. That's what the Markov chain is implicitly doing, right? And you can see this is done for every ratio. This is done for every ratio separately, right? So it kind of decomposes the problem in terms of like you minimizing your nickel cobalt separate from like your thorium scandium, right? Which is also quite a useful property. And then if you actually think about what goes into these, what's going into these values, right, into these ratios is the result from the Bootstrap, right? So into the MCMC actually goes the result from the Bootstrap. And so all of these are basically done separately, right? That if you have a rock which has thorium scandium, you're going to put it on here. But then you have a completely separate graphic for nickel cobalt, right? And if there is a ratio, if there's data for thorium scandium, but not for nickel cobalt, then it's included in the thorium scandium Bootstrap, but it's not included in the nickel cobalt Bootstrap, right? So it's not like we're setting it to 0 or something. It just does not exist in nickel cobalt because we don't have values for it, right? So there is no imputation of missing data. There is nothing like that going on. We're just using the data we have, but because of this method, it's completely separable. So not every rock has to have all the data, right? It's not like a linear regression. It's completely separated out, and therefore the missing data ultimately doesn't matter. Did that make sense? Or
yes. Okay. Yeah. Because currently in our data mining programs, we mean many things similar like that. But it's more or less similar process that we select elements according to geochemical implications, and we limit the number of elements that according to practical reasons. And it's also true that for the missing data, we also find that certain ways to treat it. Sometimes we'll get the average number, and sometimes, for example, for this situation, it doesn't matter. You just put out the ones that have elements. But
also, there are also some very clever algorithms I've read about. It's basically doing almost like PCA, but with missing PCA that's robust to like missing data. So it's like this Bayesian algorithm, which then instead of just doing the average, right, it actually gives you the value that is most expected given the other values, right? It's almost like maximizing the expectation of this because it's like this big Bayesian thing. I have to look up that paper. There was a very interesting paper I read. It basically allows you to fill in missing data, but not just with a basic value. It's actually quite an advanced way of filling in the missing data and imputing it, basically.
Yes. Okay. Do we have more questions from the audience? Sorry, as a host, I took too much time. So feel free to ask questions.
Yeah. Any more for any more? I mean, people can also feel free to ask about any of these components because I went through some of it quite quickly. Hey, if everyone understood, that's fine with me. Huh? So can you speak up a little bit? You're a little quiet. My computer is kind of bad. My good computer broke down, so now I'm on my bad computer. It's a bit quiet. It's a little bit, yeah. Sure. Yeah, there's plenty of applications for machine learning here. I think an obvious place to start would be with the LOF filter, right? Because it works. It's one way. It's one way to detect errors in your data, right? But it's not a very complicated method, right? Actually, all the equations you see are just these three equations here, right? So a good way to sort of, use more machine learning here would be you could start doing something like outlier detection, like, imagine even with something like neural networks or something like that, right? I'm not sure if you're familiar with, there is this category of neural network models, which is used on like credit card data, credit card transactions. It's used by big banks, and they use this machine learning method to detect fraudulent transactions, right? And the assumption is like, 99.999% of credit card transactions are good, but like 0.000% will be, there'll be a very small amount of just like, just fraud happening, just bad stuff. And you want these big banks, they use this machine learning to basically, the machine learning detects what's like a normal credit card consumption. That's, by a normal consumer, right? And then if it looks very different, then the machine learning algorithm will say, hang on, this looks like completely different than from a good transaction. Therefore, I'm going to say this is a bad transaction. I'm going to, send an email and warn people and so forth, right? So big banks use this type of neural network machine learning for like outlier identification. And I believe here you could say the same, you could use the same method. Obviously, this is rocks and that's credit cards, which is very different, but the algorithm would be the same, right? You give it examples of all the good rocks, right? You kind of, just go on generally what your data you expect. You can use your igneous composition for that. You train it on a data set, and then the algorithm is basically detecting, is this like one of these good rocks, or is this something that's completely different? In which case, like it is outlier. So I think that would be a very good way to use machine learning here. The other areas, bootstrapping, you probably don't want to use machine learning. And again, the Markov chain Monte Carlo, the sort of error minimization, you probably don't want. You want to stick to having your, errors calculated in a rigorous statistical way. So you probably, right, because you don't want to have you don't want a neural network to make up the error bars. You want to have statistics behind your error bars, right? So I would not touch the Bootstrap and the Markov chain Monte Carlo. But maybe if you had more elements, then you have much more combinations. So you cannot just go through all of them, all the combinations. So maybe you could use some machine learning here to just start detecting what is more promising, what is a better proxy ratio to use, and what is worse, right? So I think these two areas would be a good application for machine learning in this case. Any more questions or follow-ups on this? Also, if you were confused by my talk, then just tell me apart where you got what was most confusing. I sometimes confuse people, especially over Zoom. So I can go over something again.
Yeah, I think the paper is well written. We have read it in my own group meeting that it makes sense to us. And actually, to make a comment is that I think this in recent years we see a lot of geochemistry paper that trying to do the data-driven inversion. I think that your paper, from my own perspective, is the best one so far. That in terms of the completeness of the work, from the data selection to the data filtering, and then with the data analysis method, this is the most complete one. This is just my own opinion on it. We have read many different papers. Yeah, and then I'm sorry if the other speakers that are lecture series that heard me saying that, because they're also talking about their research. But I think it's quite obvious. Okay. With that, I think let's wrap up today. And thank you very much again, Matt, for giving us this talk and explain your paper. Yeah. And I think the audience as well, because we record this video, we post it on the Bilibili website, which is Chinese YouTube. I think there are people are going to watch it again, and especially by reading your paper. or reread your paper, which I think is really worthwhile. Good work. Okay, thank you very much, Matt.
Yeah, and feel free to reach out if you have questions or comments.
Yeah. By the way, if you could send me that paper you recommend, that other than assign average value, but to assign a value that is more likely to be the real value.
Oh yeah, the Bayesian thing. Yeah, I'll have to look around it somewhere at the back of my computer.
I'll
find it somewhere and send it to you.
Yeah. If you happen to find it someday, feel free to share with me.
Absolutely.
Okay. Great. Wow. Thank you very much. And I hope that one day you will visit Hangzhou.
Sounds like a fantastic place. I can't wait for this whole situation to clear up.
Yeah. Things won't become normal this year. Even for next year, it will be a little hard.
One day.
Yeah, one day. Great. Okay, see you, Matt.
Have a good one.